Hello fellow problem solvers. So they're going to be doing a problem which is proving the arithmetic geometric harmonic mean inequality. So this is something that I wondered when I learned about these inequalities. How do we prove these? Like, you use them a lot, but when you learn to use them initially, you don't learn how to actually prove these things are the case. So now that is what we're going to be doing today. I invite you, if you want, we'll be focused on proving these two inequalities, the AM-GM inequality, and I will leave the GM-HM inequality to you. Given you know this, I'm going to give you a challenge. Given this, prove this. Okay? So it's going to be the final challenge. And so now, if you want to try this out by yourself, I invite you to try it out for about 15 minutes at the minimum, ideally half an hour, but not more than an hour. I don't want you to get too stuck in this. This is just a way of thinking that I want to show you. So now, without further ado, let's begin. So given we are focused on proving this, where I'm going to just forget about the HM inequality, let's think about it. What is this one problem solving principle we talk about here? Well, we say that, listen, if you want to prove something general, try to prove it for specific small cases. This is a general N, a general A1 through AN. Let's try to prove it for one specific AN. Namely, let's try to prove it for N equals 2. For N equals 2, we have this is A1 plus A2 over 2 is greater than or equal to the square root of A1, A2. And we know that we can write this down. This is true if and only if the square root of A1 minus square root of A2 squared is greater than or equal to 0, which is true. We have equality if and only if these two numbers inside the square roots are equal, and they are equal only if A1 and A2 are equal. So we have this sort of basic thing proved. Now, can we prove A3? Well, for A3, we have a bit of a difficulty. This is over 3 greater than or equal to the cube roots of A1, A2, A3. Now, if we were to cube everything, we could do this. We could prove this. Potentially, maybe. Actually, I'm not even sure. What would we have? If we cubed this, multiplied this by 27, and cubed it, we would have A1 to the power of 3, A2 to the power of 3, A3 cubed, and then all those combinations of them. Now we could, and we would still end up needing to prove that A1 cubed plus B1 cubed plus A1 cubed plus A2 cubed plus A3 cubed is greater than or equal to 3 A1, B1, and A1, A2, and A3. And we would still have to prove really the same thing here. It's just with a different name. So cubing it doesn't really solve anything. It just it gets rid of the root, but we can get rid of this root by saying let AI be equal to BI cubed. And then what we need to prove is that B1 cubed plus B2 cubed plus C2 plus B3 cubed is greater than or equal to 3B1, B2, B3. And now there doesn't seem to be a very, how should I say this, a very direct, a very intuitive way as to how we should actually go about factoring this, right? So, okay, 3 seems to be difficult. Now, let's do a thing where let's forget about 3 for a bit. Let's look at 4, because we're having maybe trouble here. Maybe there's other cases we can solve, and maybe we can use something there to solve these smaller cases. And this is a more higher order problem solving strategy. Is when you can't figure something out, try to see if there's something else you might figure out on another case that could be useful on a lower case. Now, for n equals 4, what do we have? We need to prove that, let's just use a plus b plus c plus d over 4, actually this is greater than or equal to 4 times the 4th root of a, b, c, d, right? Now, can we prove this in any way, shape, or form? And the answer here is, I invite you to actually here, pause for say 5 minutes and see if you can prove this fact. Okay? Now that I hope you've paused, well look, if we apply this thing up here on a plus b, this is a question mark, right? We don't know if this is true. But we know that a plus b is greater than or equal to 2 roots of ab. And this thing right here is greater than or equal to 2 square root of cd. Right? And now, if we apply the same thing again on the square root of ab plus, we can do 2 times this, we'll have that this is greater than or equal to 2 times the square root of 2 times 2 times square root of ab times square root of cd, which is equal to this, 4 times the 4th roots of abcd, right? So, for n equals 4, we can actually solve this. And if you think about it, well, we can also solve for n equals 8, right? It's just going to be, we'll apply, so we have a1 plus all the way till a8. We'll know this is greater than or equal to, well, by this thing right here, we'll know this is greater than or equal to the 4 times the 4th roots of a1, a2 till a4 plus 4 times the 4th root of a5, a6, a7, a8. And then when we apply this thing right here, this will be greater than or equal to 2 times square root of 4 times 4, the 8th root of a1 through a8, the 4th root of this. And when you get rid of the square root, you have 8 roots of a1 through a8. Right. So now what we have is, we have this inequality proved for every power of 2. Now my question for you is, can we use the fact that this is always true, somehow, can we use the fact that this is always true, to prove that from here, that it follows that a plus b plus c is greater than or equal to 3 cube roots of abc? Can you use this to prove this? I invite you here to pause for about, say, take 15 minutes and try to think about, can you set d to something so that this thing here implies this? Pause now. And here's the next step. Okay, so now what we need, we need to set d somehow such that this thing becomes this thing, right? When we move d to the other side, then it becomes this. So let's actually set that up as some sort of like equation. I mean, that's one thing we could do. We could just like set this up as an equation. We need to have, what do we need? We need 4 times the 4th root of abcd minus d to be equal to 3 times the cube root of abc, right? That's one way of thinking about this. Another way is say, okay, wait, this thing is a to a third, b to a third, c to a third. Here we have a to a fourth, right? I need to make a to a fourth when I'm multiplied by d to be a to a third, right? So I need, in d, I need to have, what? I need to have it a to the 1/3 minus a fourth. Now what is that? Well, that is 4, 3, that is a to 1/12, right? So, what do we have when we set d to equal to abc to the power of 1/12? Well, we get that this thing right here transforms into what? We get a to the power of a third, b to the power of a third, c to the power, like this all transforms into. Actually, but wait, we have not really that. We have, right, it's not d to the, we need to have d right now is d to the power of a fourth, right? Actually, d here is d to the power of a fourth. So what we really need is to have d equal to abc to the power of a third, which then will give us what we need. So if we place d is equal to the cube root of abc, we'll have that this is equal to 4abc times a to a third, b to a third, c to a third, which gives us, so this is going to be 4 times 4 root of a to the 4 over 3, b to the 4 over 3, c to the 4 over 3, minus the cube root of abc, and this is going to be equal to 3 times the cube root of abc. So if we put d to be equal to this in the n equals 4 case, then from here we get this. Now the question for you is, and I invite you to take 20 minutes to see if you can now prove the thing for a general n. And here's sort of the next steps that you need to take. You need to say you're proving something for an n, right? For a1 through an. You want to prove the general AMGM inequality. So prove it for some 2 to the alpha that's greater than n. And then figure out, now if you know that a1 plus all the way till a to the 2 alpha is greater or equal to 2 to the alpha times the alpha root of a1 through a2 to the alpha. Figure out what you need to set an plus 1 all the way to a to the 2 to the alpha such that you get the inequality that you need. So now without further ado, I invite you to pause for 20 minutes and try to figure that out. And here's the next step. We have this via induction, we know this is true. Now we have take n less than 2 to the alpha, or take 2 to the alpha less than n. Take alpha such that 2 to the alpha is less than n. Is greater than n. And now what do we have? Then we need to set an plus 1 is equal to a 2 to the alpha is going to be equal to some x, right? We'll figure out later what this x needs to be. Now let's do the calculations. What do we have? Then from here, let's call this star. So we have from the star, we know that we'll have a1 plus an plus how many x's? We have x times, what is this? This is 2 to the alpha minus n. How do I know there's 2 to the alpha minus n things here? This is like just a tip I sort of saw once and always use. This is a n plus 1, n plus 2 to the 2 to the alpha. Now how do I count these? Oh, it's difficult. Well, if I decrease n for every single one of these indices, I'll have a1 through a to the 2 to the alpha. Like now it's like 1, 2, 3, 2 to the alpha minus n. It's just easier for me to figure out how to actually count when I do that. But anyways, back to the problem. We have this is greater or equal to 2 to the alpha times the 2 to the alpha root of x to the power of 2 to the alpha minus n, because that's how many times we're multiplying this, times all these other ones, a1 through an. Okay, now let's see, what do we actually need? Well, we need this thing right here. We need a1 through an. Like this is all to the power of 1 over 2 alpha. 1 over 2 alpha. We need this times x to the power of 2 alpha minus n. We need this to be equal to a1 to the power of 1 over n. And so on and so forth, an to the power of 1 over n. So now, what does x need to have for a1? Well, we need to have, if x is going to have a1 to the power of some, say, t, then this is going to be to the power of 2 to the alpha minus n plus 1 over 2 to the alpha, and this needs to be equal to a1 to the power of 1 over n, right? If it's to the power of some t. And now we solve for t. We have 1 over n minus 1 over 2 to the alpha is equal to t times 2 to the alpha minus n. And from here, what we get that this is 2 to the alpha minus n over n times 2 to the alpha is equal to t times 2 to the alpha minus n. These two cancel out, and you have t is equal to 1 over n times 2 to the alpha, which means what? Which means that, okay, x is going to be equal to a1 till an, and every single one of these to the power of what? 1 over n times 2 to the alpha. And then what will happen here is, this is going to be to the power of 1, 1. Then we're going to have this over n times 2 to the alpha plus n times 2 to the alpha. And let's see actually what happens when we do this. And if we've made a mistake, so the next step is, and actually we have made a mistake. I just saw I forgot to divide this by 2 to the alpha, right? So I forgot to divide this. Now we have this is also over 2 to the alpha, which changes the calculations, but it only changes them a little bit, over 2 to the alpha, which means t doesn't have a over 2. So this over 2 to the alpha, t is equal to 1 over n. So x needs to be a1 times a2, all the way till an times 1 over n, to the power of 1 over n. And what happens when you plug this in and do the math is that a1 times a2 times an times this to the power over n times, how many times we have it? 2 to the alpha minus n. We get that the right-hand side of the inequality turns into, this is going to be equal to a1 times an. The 2 to the alpha and this cancel out, and we're left with 1 over n. So that goes in here. So this is what the right-hand side is equal to. And the left-hand side, a1 plus a2 plus an plus 2 to the alpha minus n times the nth root of a1 through an, all the thing over 2 to the power of alpha. Now when you do right-hand side is greater than or equal to, is less than or equal to the left-hand side. When you multiply everything through by 2 to the alpha, these things then, this cancels, this thing cancels out with this, n of them remain, and then this implies that a1 plus a2 plus an over n is greater than or equal to the nth root of a1 through an. And this solves the arithmetic AM-GM. This proves the AM-GM inequality. And we have the equality needs to hold true, where it holds true for the inductive case. So when a1 is equal to a2 is equal to a3 is equal to an is equal to this for all these ai's. And now this proves the AM-GM inequality. And now you know, like what I like about this proof is it taught me a new concept. It taught me a new concept of like going inductively to the power of 2 and then figuring out, wait, I can go to inductively to something, have a proof for some big n, and then use that fact to figure out smaller cases. Like I can go inductively back and forth. Like, okay, I have 1, I have 2, 3, I don't have it, let me go to 4. I have 4, now I have 3. And then I have, okay, I don't have 5, 6, no. 8, I have 8, okay, now I have 5, 6, and 7. And I think this is like a really cool way to think about how to prove something in general. And it also got me an intuition for how this inequality can be proved. And why it's also difficult, if you don't know it, like for some odd numbers of n, it's very hard to use something else. Because it's like, this is the proof, and you know what the proof is, and you know that you can't really get to it by other ways. So this finishes up our AM-GM inequality. And as always, thanks for problem solving.